Let's take a look at example 4. They say that an airplane is flying on a flight path that will take it directly over a radar tracking station, as shown in the figure below. The distance s is decreasing at a rate of 400 miles per hour when s equals to 10 miles. What is the speed of the plane? So if we look at this diagram, the way that things are written, we know that the plane is flying horizontally, and the speed of the plane we can represent by the expression dx dt. It's the rate of change of its position in the x direction. That's going to be dx dt. We know that it says that the distance is decreasing at a rate of 400 miles per hour. So they're telling us ds dt, and one of the things that's very important here is the number 400. It's decreasing, so it's moving closer to the station, so that's going to make that a negative rate. That's going to be negative 400. I'm just going to leave the units off, but it's miles per hour. We want to find that speed when the plane is at a distance of 10 miles from the station. Well, if we look at this figure, the equation that's going to govern this situation is, because it's flying parallel to the ground, it's going to form a right triangle. We know that leg squared plus leg squared equals hypotenuse squared. So we can say that x squared plus 6 squared, which is 36, is going to be equal to the square of the hypotenuse, which is s squared. So we have an equation that relates all of our variables to the given information. We can now go ahead and take the time derivative of both sides. Take the derivative with respect to time of both sides. As time changes, the x position and the s position, the distance change. So x and s are functions of time. The derivative of x squared is going to be 2x, and then from the chain rule we need a dx dt. Derivative of the constant 36 would be 0. And the derivative of s squared is going to be 2s ds dt. So we're able to take the time derivative of both sides. We're asking for the change, the velocity of the plane, its rate of change. We want to solve for dx dt. So I can divide both sides by 2x. This will cancel with this. And what we will have is that dx dt is going to be equal to, these 2's cancel, and one way we could write it would be like s over x ds dt. So we now want to solve for dx dt. Let's plug in what we know. We want to solve it for when s is 10. We know that it's decreasing at a rate of negative 400. So that's our ds dt. But what we don't have at this moment is x. They didn't tell us what the x value was. But we should be able to go ahead and solve for this. If we look at our right triangle, at that particular point in time, so it looks like this, we know it's flying at a constant altitude of 6 miles above the ground, and we know that s is 10. So to solve for x, we can use Pythagorean Theorem. Leg squared plus leg squared equals hypotenuse squared. X squared plus 36 equals to 100. X squared equals to 64. Take the square root, we would get x equals to 8. So we get x equals to 8. Let's go ahead and work this out. It's going to be 800. It's going to be 8 divided by 10 times negative 400. That should be negative 500. That's going to be miles per hour. So negative 500 miles per hour. Okay. In terms of the speed of the plane, if the question is just like how fast the plane is moving, the speed technically would be just 500 miles per hour. Okay, so remember, speed is the absolute value of velocity. The velocity gives us both magnitude and direction. So the proper answer to this question, and I should write it out in sentence form, but I'm not going to, is that the speed of the plane is 500 miles per hour. The reason why we have this negative rate for dx dt is if you look at this x variable is measuring the distance between the vertical position of the tower to the plane. Well, as the plane gets closer and closer and closer to the tower, that x distance is decreasing, and hence that's why we see the negative sign on dx dt. Let's take a look at example 5. In example 5, it says, find the rate of change in the angle of elevation shown in the figure below. So it says, a television camera at ground level is filming the liftoff of a space shuttle that is rising vertically according to the position function s equals 50t squared, where s is measured in feet and t is measured in seconds. The camera is 2,000 feet from the launch pad. So we have some angle theta here, which is the angle of elevation. See if I can get my, there we go, my pen back. So let's call this angle theta. This is going to be the angle of elevation. And we want to find the rate of change of this angle. So obviously as the rocket ship goes up, that line of sight is going to be increasing, and so d theta dt will be increasing. So we want an equation that's going to relate all of these variables. In particular, we need one that's going to involve our angle theta. And if we know s, I can already replace s. We know s is what, 50t squared. We might as well go ahead and use a angle theta. We need a trig function here. I have information about this side because we know its equation, and it might make sense to use this side here because it's a constant, and we know that computation-wise, constants are pretty easy to work with. If we know the opposite and we know the adjacent, then that would be grounds for setting up a tangent equation. The tangent of theta is equal to the opposite, that's 50t squared, over the adjacent, which is 200, or we can say that the tangent of theta is equal to, let's think of this as a coefficient times t. So we have t squared, and then 50 divided by 2,000. If we simplify that, that should be 1 over 400. It's going to be 1 divided by 40. So this will simplify to 1 over 40. So we have our equation. We want to find the rate of change with respect to time of theta. That's d theta dt. So let's go ahead and take the time derivative here. So we're going to take the time derivative of both sides. Take the derivative of the left-hand side. We need to take the derivative of the right-hand side. We recall that the derivative of the tangent of theta, that's secant squared theta. And then from the chain rule, because theta changes with respect to time, we need to multiply that by a d theta dt. On the right-hand side, the derivative of 1 over 40t squared, that would be 1 over 40 times 2t, which would reduce to 1 over 20t. We can go ahead and solve for d theta dt by simply dividing secant squared theta to both sides. So we would get that d theta dt is equal to, and in an attempt just to kind of write this as cleanly as possible, I can put the t on the top, keep, change, flip. You would get a 20 times secant squared theta in the denominator. So this is our expression for d theta dt. And now we just need to plug in our variables. We want to find d theta dt at 10 seconds. So t is going to be equal to 10. But now we need to take the secant squared of theta. So we need to know what is the value for the secant of theta. Well, let's go back to our drawing here. So here's what we know. This is always 2,000. So the camera is located 2,000 feet from the launch. This side here, S is equal to 50t squared. And we know that t is equal to 10. So we can plug that in to find the length of this side. 10 squared is 100, and 100 times 50 would give us 5,000. So this side here would be 5,000. And then good old Pythagorean Theorem will help us to solve for r. The hypotenuse squared is equal to the sum of the squares of the legs. That's 2,000 plus 5,000 squared. We can simply plug this into a calculator. 2,000 squared plus 5,000 squared. Tell you what, instead of using calculator work, let's get a little bit slick about this. Or do I want to not? Yeah, let's play with algebra for a little bit. I mean, you can just throw this in your calculator. 2,000, I know, is the same thing as 20 times 100. Now, I'll tell you what, let's not mess around with this. You can do this by hand. It's not too hard to do. But if I just plug that in, here's what we would get. Get 29, and then we're going to have 1, 2, 3, 1, 2, 3 zeros. This we can write as the following. This is 29 times 10 to the 6th. And now to solve for r, we would take the square root of both sides. And the square root of 10 to the 6th would be 10 to the 3rd. So this ends up being 1,000 times the square root of 29, if you wanted the exact answer. Did I do that right? Let me just quick check. Tell you what, let's not play around with this. Let's just go for the approximate answer. If you want to, if you have time, you can do this. But r is simply going to be the square root of that number. 1, 2, 3, 4, 5, 6. So r will be the square root of give me 1 second here. It's going to work out to be about approximately 5,385.16. So that's our r, about 5,385.16. And then recall that the secant is the ratio, it's reciprocal cosine. Cosine is adjacent over hypotenuse. So this would be hypotenuse over adjacent. So our secant of theta is going to be that 5,385.16 divided by 2,000. And then that's going to go over here. And now let's go ahead and plug it in. we'll find that d theta dt, remember, don't forget in this fraction that has to be squared. It's going to be 1 divided by 5385.16 divided by 2000 squared, which works out to be about 0.07. And angles are measured in radians, and time here was measured in seconds. So it'd be approximately, d theta dt would be approximately 0.07 radians per second. And I kind of regret not doing the exact value for r here. Again, you can use your algebra, write r as a simplified radical and then plug it in, and you would get the exact value for this. Typically with these applied problems in WebAssign, they're going to want you to round. Just be aware that, if you round an answer earlier in a problem, that rounding error would be compounded as you do further calculations with it. So, just take these values, these intermediate values, out a few more places. I would say 5-6 decimal places should be sufficient. But for this one, we have our answer. D theta